Morning, students. There's been a lot of requests that I go over the vector quiz. In fact, I've had a couple students, that were emailing me over the Zoomless days, asking for help with this problem, this problem, this problem, and I did. I was able to do that. And then I had another couple students that said, well, can you just go over the quiz in class today? And that's not really an option, just because we're so behind in content. I can't take a whole Zoom and go over this. So instead, I thought I'd make this video real quick. Hopefully you'll find it useful. So here we go. Vector quiz should look familiar to you guys. Keep in mind this is based on that worksheet that we did earlier this week, and I did take a little bit of time to go over. But hopefully this will make a little more sense. It says determine the x and y components of the following vectors. And it also says don't forget to set your coordinate system. Now, a coordinate system in a math class is just x and y. Or you've probably heard of a coordinate plane, the x and the y-axis. But a coordinate system in a physics class, depending on the problem, sometimes your coordinate system is up is positive, down is negative, and that's it, if you're dealing in one dimension. Sometimes maybe your coordinate system is on a slope. If you're going down a hill, sometimes it's easier to turn that coordinate plane and have it go down the hill. But for this problem, I'm just going to keep it simple. We are dealing with, x and y axes that are just lined up. This is the positive y-axis. This is the positive x-axis. There you go. And not just the axis, the direction. So as we look in problem A, this is going down and to the right. Okay, hopefully you guys can see what I mean by that. So that's the resultant vector that they've given us. And it's pointing down and to the right. So it would make sense then that our component vectors go to the right and down. Now notice, when I make these component vectors, I'm drawing them tip to tail, which means if I end one vector like this, the very next vector's tail is going to start where that one ended and go to the next one. Wherever the next vector is, the tail is going to start there and go to the next one. So we draw them tip to tail when we're doing components or when we're adding together several vectors. So anyway, I've done that. Let's take a look at this. The red one is our x vector because it's in the x direction. It's horizontal. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. And because it's to the right, okay, I'll write down 9 units. But because it's pointing to the right, we are going to call that positive 9 units because it's in the positive x direction. That's what we've got over here on our coordinate system, okay? Now with our blue one, 1, 2, 3, 4, 5, 6, 7, 8, but this one's pointing down. We just defined the positive y direction as being up. So if this one's pointing down, this is going to be a negative 8 units. I think it was 8. Yeah. Okay. That's that one. Let's look at B. All right. In B, we see this resultant vector is pointing up and to the left. So it should make sense then that our individual components are going to point left and up. Left and up, just like this. Or up and to the left. I mean, it's the same thing. But notice how I'm drawing these vectors. That's really important. Some students continue to just like write these as lines. These are not line segments, guys. These are vectors. They have magnitude, which means length, but they also have direction, so make sure you draw them that way. All right, so my y vector is 2 units. Because it's pointing up, I can see on my coordinate system over here that up is positive, so I'm going to make that positive 2. But with my x, it is pointing to the left at 8 units. And because it's going to the left, that's going to make this a negative 8. And that's all there is to number 1. Let's look at number 2. For the following, determine the resultant vector using vector addition. So vector addition basically means you're drawing all the individual vectors tip to tail, tip to tail, tip to tail. But then when you draw your final vector or your resultant vector, we're always going to draw it start to finish. So let me explain what I mean by that. So whenever you're doing a resultant vector, you're always going to go start to finish. So what that means is, we look at A. If you start on the bottom right of that graph or coordinate plane and you end kind of up and to the left of that, then your resultant vector should be pointing up and to the left. And so when I draw my resultant vector, this is going to be so pretty. Nope, I can do better than that. When you draw the resultant vector, nope. There we go. That's a little better. It needs to be pointing up and to the left. And again, it's not perfect. Actually, I could probably move it. Let me see. See if I can move it. Make it look a little bit better. There we go. That's about as good as we're going to get. So if it's pointing up and to the left, that's how I want to draw it. Usually when I draw resultant vectors, I do like to fill in the head of the arrow, the tip, and that's what we're getting here. So we draw it start to finish. So that means that we started down here, finish is up here, start to finish. If we look at B, I'm going to go ahead and draw this one while I'm at it. Start down here because we start at where that arrow begins, and where the last arrow ends is going to be finished. So when we draw start to finish up here, there we go. And so there is our resultant vector. Okay, let's draw our individual components, because the thing is, that's not the answer. You know, you can't count the length of these, and we're going to need direction in a moment anyway. So we still have to find components. Now I'm going to use the same coordinate system as before. It's not going to actually matter as much, but when I draw my individual vectors, I'm still going to make sure, like if the arrow is going up and to the left, then my individual components better be up and to the left, which is what I'm doing right here. Now I'm going to count these up real quick. Basically what we're trying to do is we're trying to create a right triangle, because as soon as we get a right triangle, then we can actually get down to business, okay? We can use trig, we can do whatever we need to do to solve for what we're missing. X is 1, 2, 3, I think it's 10. Yeah, so this is 10 units right here, and I know what you're thinking, well, Mr. Nairn, that's pointing to the left, isn't that negative 10? It is, and if you want to put a negative, you can. The fact is, if you're dealing in two directions at once, you know, we're going to try and find the magnitude of the green arrow, the resultant vector. We're not going to be as cut and dry as just positive, because the thing is, it's positive in the y, it's negative in the x, and so that's why we're going to do our direction, okay, with theta. And so this one we have to be a little more specific. So instead of just positive or negative, for this one we actually have to use theta to tell us what the direction is. In fact, that's what it says up here, use a degree direction, and that's what we're going to do. So I've got 10 and 4. I'm going to use good old Pythagorean theorem, which means in my calculator I'm going to do 4 squared plus 10 squared, and then I'm going to square root that value. You guys should know Pythagorean theorem, okay? That's one of the things that you definitely learn between middle school and now. And I got, I don't know, roughly 10.8. In fact, I can go and write that down here. That's the magnitude. It's 10.8. But when we're doing direction, let me use orange, I guess, I have to use theta. Now, I am going to define theta from the bottom right-hand side of the graph, because that's where the vector is coming from. Okay, that's where it's coming from. And so this is going to be my angle theta. And I'm just going to say theta equals down here. That's what we're solving for. Now, I have 4, I have 10, I have 10.8, I have all this information. So technically you could use sine, cosine, or tangent. I am going to use tangent. And the reason why, there's less error associated with that. Like I have opposite, 4 units. I have adjacent, which is 10 units. And by the way, that's what tangent is. Okay, if you've forgotten, tangent of theta, is equal to opposite over adjacent. But the inverse tangent is what I'm doing, is opposite over adjacent equals theta, and that's what we're doing here. So the reason I'm using 4 and 10 instead of the 10.8 is 10.8 is a calculated value, and so that you're going to get not the wrong answer, but it's not going to be as right as if I use the two values that have less calculations associated with them. So I'm going to do inverse tangent in my calculator. I do second tan. That gives me tan to the negative 1 of 4 divided by 10, and I get 21.8. So there you go. 21.8 degrees is what we're looking for right there. Let's look at B. So B, I'm still going to do components, same as before. This one is pointing up and to the right, so it should make sense then that my vectors are going to point up and to the right, like so. My red arrow is 1, 2, 3, 4, so that's 4 units here. My blue arrow is 1, 2, 3, 4, 5, so I'm going to put a 5 over here. And so, again, to find the magnitude, I'm just going to use Pythagorean theorem. So I'm going to do 5 squared plus 4 squared, square root that value. And I do hope that you guys will try this in your own calculator so you can see where I'm getting these numbers. Don't just trust me, you do it. And I got 6.4. So magnitude is 6.4, but now we also need a direction. So what I do, So I'm going to say, all right, this is theta. Once again, always define theta where your resultant vector is coming from. Not where it's going to, where is it coming from? That's typically why I pick theta as being right there. So theta, same as before, I'm going to use tangent. And so I'm going to say, all right, well, inverse tangent of, what's my opposite in this case? 5, all right. Units divided by my adjacent, which is 4. Okay, that's what's right next to theta. That's our adjacent. So 4 units. Let me do that in the calculator. Second tangent, 5 over 4, and I get 51.3, and OneNote just crashed. So theta, let's try this again. Theta is 51.3. And so I'm going to write that as 51.3 right here. Just close it, that's fine. And I'm recording a video, I shouldn't be too much longer. So I get 51.3 degrees, all right? And again, when you guys are defining theta, you can say theta equals 51.3. You could say 51.3 degrees from positive x-axis, because that's what it is. You could also say 51.3 degrees north of east. There are multiple different ways that you could define this. In fact, you could also, now don't get too confused about this, but basically, you could also define another theta. I mean, what if I define theta as being right here? I could do that. Depending on how you drew your coordinate system, you could define it that. So maybe instead of being 51.3, you could also say theta equals 38.7 degrees. And then you could say, oh, well, this is going to be 38.7 degrees from the positive y-axis. Or you could say this is 38.7 degrees east of north. Okay, so there's a couple different ways you can do it. I personally like 51.3, but technically either way is correct. Number 3, a man's rowing a boat. Okay, and by the way, this is a good problem, wink wink, if you know that there's a test coming soon. This is a good problem to know. Let's look at all the information. He's rowing a boat at 20 meters per second east in a stream that's flowing 15.0 meters per second south. Draw a picture illustrating the interacting velocity vectors, then determine his true velocity. So, coordinate system in this one, it's really going to be north, south, east, west. I mean, we're not really dealing with x and y, we're dealing with north, south, east, west. So if I'm saying 20 meters per second east, maybe this is how I draw it. And if I don't like it, I'll redraw it, but I think this is going to work. 20 meters per second east. Okay, and you can even put an E next to that if you wanted to, or the fact is we've got that coordinate system defined over on the left. You can just leave it like that. And the stream is flowing 15.0 meters per second south. So notice, I referenced the coordinate system. I made it 20.0 meters per second east, and then I made it 15.0 meters per second south. I have arrows that are pointing the correct way. So now, all we have to do is determine his true velocity, or it's a man. So here we go. Start to finish. Told you guys that a couple times in this little video. We're still going from the start. And again, I know this isn't dealing with position. This is velocities. But you still draw from where you started your vector addition, up here on the top left, to finish down here. So don't get too confused about it, but that's still what we want to try and do. Pythagorean theorem. So I'm going to say, all right, 20 squared plus 15 squared. And I'm going to do the square root of that. And I get 25. And actually, this is technically a 3, 4, 5 triangle. If you look at it, of course, there's an announcement. Hold on one second.
Whitney Roberts, call extension.
Thank you, Miss Austin. So anyway, we've got 25.0 meters per second. It's 0.0 because of sig figs. Not like we're really paying too much attention to that. But if it's 25.0 meters per second, we've got this, all right? Once again, we need to also determine an angle. And so I'm going to say, all right, here's my angle right here. Okay, so this is going to be theta. Same as before, guys. It's the same thing over and over again. Opposite is going to be 15. Adjacent is going to be 20.0. And this is going to be equal to theta. So I'll type that in my calculator. And I don't know if I mentioned it earlier. I know that a lot of math classes like to use radians. When you guys are doing problems for my class, you should always be in degrees. And so right here, I get theta equals 36.9 degrees. So my final answer, and I'm going to write it all together, my final answer is going to be 25.0 meters per second at, let's just say theta equals 36.9 degrees. That is the correct answer, okay? And if you just give me just 25, that's incorrect. That's wrong. But if you say theta equals 36.9, now, I say, okay, that's a vector. Remember, magnitude and direction. Number 4, because I got to wrap this up because I got students coming in. It says a hiker walks 10 miles north, 6 miles west, 5 miles south. What is his total displacement? I'm going to use the same coordinate system as before. I'm going to rewrite it for every problem that I use it, just because it's nice to have it there as a reference. And when I'm grading it, that's something I'll start to look for if we get to that point this semester. Okay, so 10 miles north. Here we go. I'm going to draw a nice long vector because this is going to be 10 miles. Next one is 6 miles west. Oh, man. I'm going to move this over. Forgot we're going west. There we go. Next one, 6 miles west. So I'm going to draw this one a little bit shorter. 6 miles is not as far as 5 miles. I know that's complicated. And then I'm going to draw a little short one, kind of coming down about halfway. There we go. And this is going to be 5 miles south. Drawing a picture is going to be critical for a lot of the vector problems that we do, and this one's no different. So we got 10, 6, and 5. But again, if we're looking for total displacement, we're still going to draw start to finish. We're still going to go start to finish. So finish is up here, start is up here, or down here, and so when I draw start to finish, that's where it needs to go. So it looks kind of like this. And then, guys, it's the same thing that we've been doing. So now I can say, all right, well, he's from start, technically he went up a little bit, went north. Does that make sense? He was further north than where he was at the beginning of the day. And also, he went west. He ended up further west than he was at the beginning of the day. So I'm still making an X and Y component, which is what you have to do. And look, I'm just making a right triangle. So now that we have a right triangle, we can start to look for some stuff. So I know that this red one at the bottom is 6 miles, right? Because that corresponds to what's up here at the top. So that's 6 and that's 6. And I also know that this blue arrow over here is going to be 5 miles. I mean, you got to just look at the way I drew my picture. If he went 10 miles up, but he came back 5, he only went 5 north. And so that's how I end up getting this. Now it's Pythagorean theorem, everyone's favorite. So 5 squared plus 6 squared. I'm going to square root my answer, and I get 7.8. Yeah, I'll just keep it at 7.8. So I get 7.8 miles right here. That was the total displacement. Now I know what you're going to say, but Mr. Aaron, he walked 21 miles. I know, that's different. We're going to learn about that soon. But if I'm saying displacement, it's going to be 7.8 start to finish. Next thing we got to do is we have to find our angle theta. I'm just going to identify theta as being right here. Once again, when I identify theta, I always want it to be where the vector is coming from. And so that's what I've done right here. All right. Now, finding theta, same old song and dance. Inverse tangent of opposite, okay, which is 5. It looks like an S, but it's a 5. Over 6, which is the adjacent, okay. So inverse tangent of 5 over 6, and I got 39.8. So theta equals 39, equals theta. Theta equals 39.8. There we go. Now we're all caught up. So let's write our final answer. Whenever you guys write final answers, you should always do that and then box your answer. For this problem, because we're dealing with north, south, east, west, I think I'm actually going to do this one in terms of degrees based on a compass. So this one's going to be 39.8 degrees, but then I want to say that's technically north of west is how you would want to report that. And if you're having trouble with that, we can maybe talk about that another time. Number 5, as we wrap this up. It says 2 people are pulling on a rope, one with a force of 20 newtons to the left, and another with a force of 20 newtons to the right. So it says, what is the resultant force between the two? Well, guys, if you just draw this picture and say, well, one's pulling 20.0 newtons, by the way, that's what N stands for, 20.0 newtons to the left, and another one's pulling 20.0 newtons to the right. Guys, if you add those two together, I mean, they're going to cancel each other out. Okay, nobody's going to go anywhere. So the resultant force between the two is going to be a whopping 0 newtons. That's the resultant force because they cancel each other out. Hopefully OneNote will load here in a second. There we go. What would be the resultant force if a third person began pulling from the center of the rope perpendicular to the other two with a force of 30.0 newtons upward? Now this one's kind of tricky. I'm going to move my drawing. Hold on, announcement. So as I was saying, I'm going to move this down here. And so it said they're pulling upward, okay, from the center. So let's say it looks something like this. And this is getting to be kind of weird, but this is going to be 30.0 newtons. I tried to show that it's 30 by drawing this a little bit longer than the other two. And so resultant force now, you've got to think, the 20 and the 20 are canceling each other out. So the only thing that's not getting canceled out, basically the x direction is null. Okay, there's nothing going on in the x direction because they're canceling each other out. But we have a positive 30 newtons in the positive y direction, right? And so my resultant force is going to be positive 30 newtons in the positive y direction. And that's all there is to it. And I recognize problem number 5 is kind of weird, but it's still good to think about. All right, guys, hope this was helpful. If you've watched the whole thing, you should definitely be updating your quiz and sending me an email.